Okay, welcome back. So this will be the last lecture of our module 3 pairwise sequence alignment, and today we are going to discuss two topics, that is, one is database searching and the second is how do we know the significant statistics of alignment. So far we have looked at many alignment methods based on edit distance, global alignment, approximate pattern matching and local alignment. And specifically in the last lecture we also looked at how do we consider gaps in the alignment. Now as a result of these algorithms we have a powerful tool available now which is known as database searching. So this is a key example of how these algorithms have empowered important biological applications. So now with the help of additional heuristics on top of these dynamic programming algorithms, we can now do searching in large databases which have molecular sequencing data. So these heuristics that allow us to scale to large databases will be looked at in the next module of this course. But so with this heuristics, what one can do is we can scale these alignment algorithms to large databases which have either trillions or even petabases of data. Now one of the popular examples that I keep using in my course is the BLAST software, which allows you to search for DNA as well as protein sequences. Now in the database searching, BLAST is one key example, and as I mentioned earlier that in this tool you can enter any sequence that you want. For example, if I have a sequence that I want to search in a database, then I can paste it in the text box and this tool will search for that sequence in a selected database. So if you do that, now it will also ask you to provide what database do you want to search that sequence in. So for example, there are many databases that this tool supports. For example, the first one is nucleotide collection, which is the collection of all non-redundant DNA sequences from all species that have been sequenced. Similarly, you can see many other databases such as RefSeq, assembly databases, EST databases, SRA databases and so on. Now as an example, this nucleotide collection database, so this nucleotide collection database for example contains 100 million sequences and over 1 trillion total bases. So for example, if you add up the length of all these sequences, it adds up to more than 1 trillion bases. And this database continues to grow, so it is periodically updated with newer sequences and it is growing rapidly as well. So this tool is now a powerful mechanism where you can search for any new sequence that you may have and you can search it against the entire data corpus. So for example, if I put my sequence of interest in this database, then it's based on a cloud service in which a job will get scheduled on the cloud and it will start the timer and it will ask the user to wait. So it will ask the user to wait for a few seconds until that search is completed. Now after a few seconds you would notice that the tool will output a bunch of results. So it will find, let's say, a few hits in the database and it will give them in a list manner one by one, and this list will be ranked based on the alignment score. So for example, the high quality alignments will be ranked above and the lower quality or the lower scoring alignments will be ranked below in the entire search. Very similar to how Google works. So similar to how Google ranks the top query at the very first option, this tool will also give you the most relevant hit in the first few examples. Now the sequence that we had uploaded for this example was a mitochondrial sequence from human genome, and as you can see it is able to find that searches in the searching algorithm. Now if we click on one of these sequences, let's say if we click on one of these hits, then it will show us additional information. For example, it will show us how the alignment looks. So, given my query sequence that I had given, and given the sequence in the database, it will show me how the query sequence is matching against the database sequence. And in this case, you can see that it has 100% match based on the query sequence I had given. So, this particular example, it has 100% match, and it is showing me the complete alignment end to end. So, there are various mechanisms in which this alignment can be visualized, and this tool supports various visualization methods as well. Now, given this mechanism, so now you can imagine that this kind of database searching method can be useful for various applications. For example, one simple application could be that if we suppose have a previously unknown gene that we found in a mouse genome, and then to know the relevance of that gene or to know what the function of that gene is, a scientist may take that sequence and put it in a searching algorithm and search it against the entire human genome. So, that would tell us whether the humans are also carrying a similar gene or not, and that will give us immediately some idea about what that unknown gene might be doing, what would the biological significance of that unknown gene sequence. So, that would be a very trivial example. A more recent example would be a paper very recently published in Nature, where the authors were able to do a petabase scale database searching of RNA sequences. So, they took a RNA gene sequence, which is RNA dependent RNA polymerase sequence, and they searched that sequence in all 6 million samples that are available, that add up to 10 petabases. So, that search resulted in 10⁵ novel RNA viruses that were discovered in the entire database. So, this particular search was done using AWS cloud, and the authors reported that this search was completed in 11 days using a total cost of 24,000 compute hours. So, the total cloud computing cost was $24,000. And again, this is a very recent example of a biological discovery being made by searching in a database. So, this gives you an example of how important these alignment algorithms are and how these database searches are important for biological discoveries. So, now given this context, what I want to discuss in the subsequent part of this lecture is the statistical significance of alignments. So, observe that we can always compute and report alignments of any two sequences, even if they are random. So, for example, if I am computing local alignment, which is basically asking for the highest scoring alignment between substrings of both sequences. So, I am over all possible substrings. So, there you can imagine that even if I feed random sequences, I am very likely to get a positive local alignment score. That is, I will see some alignment in which there are some matches occurring, and that could happen just by pure random chance. So, even within random sequences, I can expect to see some level of similarity in the alignment as well, because ultimately our optimization will give us the best possible alignment, and it does not care whether the sequences are actually biologically related or whether they are random. Now, then the question comes, how do we know whether the highest scoring alignment has been obtained purely by chance, or is there any biological relevance? That is there any true homology between the two sequences at all, or is it just by chance? So, by homology we mean that the two sequences share some common ancestry in the evolutionary history. So, how do we distinguish between these two? Well, maybe intuitively what comes to mind is maybe we should check the alignment score and see if it is high enough. Now, what high enough means, that we have to see in the later slides, but that is the intuition, that we have to maybe see how strong the alignment is, like how many matches are involved, how many mismatches and gaps are involved, and so on. So, if there are too many matches and the alignment is significantly longer, then intuitively we can expect that the alignment, it is not likely to happen by chance. Whereas maybe if alignment has too many mismatches, or if the alignment is too short, then maybe we can say that that happened by chance only. So, how can we take a decision mathematically? Can we use some statistics to guide us in this process? Now, here is one example where you see many matches in alignment. So, this alignment has a very good alignment score, and in this case we do not need to worry about statistics in fact. So, one can expect that this kind of alignment should happen only if the sequences have true homology. But we may encounter certain examples where the situation may not be too clear. For example, in this case I am showing you alignment of a human protein sequence and comparing it to C. elegans, which is a worm, and its TRA2 protein sequence. And in this particular case I can see that there are some matches, but it is not a strong similarity. So, there are many mismatches as well, and this is the case where we would want to know that can such an alignment occur by random or not, or whether my alignment score is statistically significant in this context, and that would maybe inform that whether these two protein sequences are actually homologous or not. Now, it will not give a concrete yes or no answer, but at least it will give us some subjective idea that whether how confidently we can say whether these two sequences are actually biologically related. Now, so given this idea, so to answer this we need to know how high a score can be achieved due to pure chance alone, right. Okay. Now, it turns out that in case of local alignment problems, there is good amount of theory developed in the literature that has studied the distribution of those alignment scores happening between random sequences. So, the statistics for the alignment scores of local alignments under random models are well studied in the literature. Now, the simplest model that has been well characterized is where we assume that the space characters or the alignment gaps are absent. So, in this case we will assume that the alignments do not have any gap characters in them. Observe that if you do not have any gaps in the local alignment, then the local alignment basically consists of equal length substrings from both sequences. So, if you have a local alignment between a substring of sequence 1 and a substring of sequence 2, then if there are no gaps, then these two substrings must be of equal length, because we must be having for every character in this top sequence we should have a alternate opposite character from opposite sequence as well. So, in this case we know that if we do not consider gaps and if we assume that the alignment does not have any gap, then the output alignment, the local alignment must have two equal length substrings. Okay. So, under this assumption let us move forward. We will define something known as high scoring segment pairs, which we will abbreviate as HSPs. Now, HSPs are the set of segment pairs or substring pairs between two sequences whose scores cannot be improved by extending the substring or trimming the substring. So, for example, if I have a HSP between two sequences, then what I am saying is that the alignment score cannot be improved further if I extend this strings further, or if I trim this sequence further. So, in some sense it is maximal segment, in the sense that I cannot further expand it and I cannot further shrink it as well. So, this is I am defining it as a high scoring segment pair. So, to show a concrete example, here is one example where let us say I look at a short substring between two sequences, let us say of length 3. In this case the alignment score is 12 based on the scoring system we are using. Now, if I expand further, turns out the score improves. So, then we should keep expanding and testing. So, if I further expand, the score further improves, but if I further expand this time, then the score has decreased. So, compared to previous time, the score has decreased now, which means that my this substring pair is my high scoring segment pair, that is HSP. So, this is an example of what I mean by HSP, and if you observe that the goal of these tools like BLAST is to report such high scoring alignments, that they are reporting these high scoring local alignments that cannot be further expanded and that cannot be further shrunk to further improve the alignments. So, by using various heuristics they are able to compute such local alignments between the given query sequence and target sequences available in the database. So, going forward what we will be doing is we will be looking at these HSPs in two random sequences. So, for example, how many high scoring segments can we obtain above a certain score threshold between two sequences that have been randomly generated, and that will give us some statistical significance of the alignment that we are actually getting from our database search. So, this theory was developed by Karlin and Altschul in 1990. So, this is I have cited the paper below. So, in the theory what they derived is the expected number of HSPs with alignment score at least S that are found between two random sequences, and they derived this expression and computed this expression as Kmn times exponential raised to power minus lambda s. So, this is the expression that they derived in the paper. Now, in this expression S is the alignment score that we are setting as a threshold, K and lambda are parameters that are dependent on the alignment scoring system. So, depending on the pairwise alignment scoring system that you are defining for match, mismatch, gap, etc. So, these are the parameters that would depend on those scoring system being used. M and N in this formula are the sequence lengths. So, M is the length of your random query sequence and N is the length of random target sequence. So, for two random sequences, this formula gives us the expected number of high scoring segment pairs that have alignment score at least S. So, this formula right now is defined for two sequences, but if you want to extend it to a complete database that has multiple sequences and there you want to know how many HSPs can we find in the entire database, then we can replace this target sequence length, that is N, with the length of the entire database. So, that would be the sum length of all the sequences present in the database, right. So, this expression gives you the expected number of high scoring pairs that exceed the alignment score S. Now I am not going to show you the derivation of this expression. For that, if you are interested, you are welcome to read the paper. I am just going to state the results that were developed by this method. So this expression gives you the expected number of HSPs. Now it also turns out that we can also normalize the alignment scores, so that normalizing the alignment scores may be helpful, because I can then compare the E values, that is these E values, between database searches where I am using different scoring matrices. So in that case, what I can do is I can normalize my score based on lambda and k parameters, and I can obtain a revised score which is commonly referred to as bit score in the literature. And with this bit score, I have now an expression of E which is independent of lambda and k parameters. So now if I am doing two database searches with, let us say, different scoring parameters, I can directly compare these E values to see which of them is giving me more statistically significant alignment. So you can imagine that lower the value of E, the more statistically significant the alignment is, because this E value is giving me the expected number of HSPs that can occur between two random sequences. So naturally, if I am doing a database search, and if I also compute the E value for those M and N values, and if those, depending on the score I see, I would want to see a lower E value, because that would make my alignment more statistically significant, right. One more conclusion that was developed by the authors was that the number of HSPs with score at least S. So now we are not looking at the expected number of HSPs, we are actually looking at the total number of HSPs with score at least S. Then this is described by a Poisson distribution, that is the probability of finding exactly X number of HSPs with score greater than or equal to S is given by the Poisson distribution given here. Now from this expression we can easily see that the probability of finding 0 HSPs with score at least S is e raised to power minus capital E, that is by just plugging x equal to 0 you can simply get this value, and immediately we can observe that the probability of finding at least one HSP is simply 1 minus the same value. So that would be 1 minus e raised to power minus capital E, and this gives us the p value associated with the score S. So that is the p value gives us the probability of finding at least one alignment that exceeds the observed score S. So under the null model, what would be the probability of observing alignment that has score S or better? So that gives me the p value. So this theory can be used in practice. So many algorithms including BLAST use the theory developed by this paper to also suggest what are the E values and P values along with the database search, so that users can interpret the statistical significance of the alignments and try to understand whether the alignment found is actually statistically significant or not. So as an example, if you feed, for example, as I mentioned that we can feed the sequence in this text box, and this algorithm will give us the database hits. Now along with the database hit, it will always also give you the E value. So corresponding to the score that we found, so corresponding to the alignment score, it will give us the E value, and that E value will guide us whether the observed alignment score is statistically significant or not. So in this particular example, because this alignment is very high quality, because you can see that there are many matches involved and the score is very high. So, therefore, the E value is actually very small. So, that is 2 E raised to power minus 73. But if this E value is large, then your threshold that you may have, then you can expect that maybe the observed alignment is statistically insignificant, and maybe we should ignore that alignment and not call that a valid hit in the database. So, one last question is that what E value cutoff should one use, right. So, unfortunately there is no definite answer to that question, and it really depends on what is your target application that you are considering, what type of sequence you are aligning, and what is the sequence length, and so on. It also depends on how, whether you want really strong alignments to your query, or whether you are willing to look for distant matches as well, and all these things will guide on what E value cutoff may be useful for your particular application. Now, a general guideline that is available online is that if your E value is significantly smaller than 10 times E raised to power minus 100, then that pretty much means that the sequences are identical, and you would see long alignments across the entire query length and your target sequence. As the E value decreases, you will see that, for example, E value greater than 1, then what the recommendation is that these protein sequences are most likely not related. That is, E value greater than 1 means that there is at least one sequence in the database that would have been found just by chance. So, therefore, in this case the proteins are most likely not related is a general recommendation, and if your E value is greater than 10, then the hits that you found are most likely junk, unless your query sequence is very short. So, for very short queries it is extremely hard to tell whether your alignment are statistically significant or not, or whether they have biological relevance. So, for short sequences it can be tough, but yeah. So, in this case one can assume that most likely the database hits that we found are most likely junk. So, this concludes the database searching and statistical significance of alignments. So, also this concludes our module on pairwise sequence alignment. Now, I briefly mentioned that sometimes these databases that we are aligning against can be very large. So, for example, we already saw examples where the database has trillion characters, and sometimes even we saw database situations where there are more than 1 petabase characters. In those cases, the dynamic programming algorithms that we have studied so far are not directly scalable to those entire databases, and there we need some help of some heuristics that can guide us to scale to large databases, and some of those heuristics are also used in the BLAST database. So, the BLAST tool that we are seeing so far, some of the heuristics are also incorporated there. So, in the next module we are going to look at the heuristics used for sequence alignment and look at how they help in scaling the alignment algorithms to large databases. Thank you.